in the previous lecture, we talked about how to find the line integrals. We now have work done in the spaces. We say the work done in XYZ space. We say given a vector field, if we have given a vector field in R3, which is f of XYZ, which equals to P of XYZ I plus Q of XYZ J plus R of XYZ K. Here, acting on a moving object from initial point A to destination point B along curve or path C, given by the general vector valued function R. This is the curve or the path that we want to move the object from point A to point B. We say the line integral for this vector valued function, for this vector field over this path is called work done by, it's called work done. Here we say the line integral for the vector field over this path. This is the curve. The curve is given as a parametric equations. Okay. Here we have given parametric equation, which is the curve, and this is the vector field. We say the line integral for that vector field over this parametric equations, I mean over that curve, is called work done. That means it's the same as what we did before. The line integrals that we found before for the parametric equations, I mean, if the curve is a parametric equations, it's the same as to say work done. Okay, it's the same as we did before. Here, work done is the integral of f dr over C over the curve C. Here, R is this parametric equation, and dr here is dxi plus dyj plus dzk. And work done is Q of xyz dx plus Q of xyz dy plus R of xyz dz. It's the same rule as previous. Here, when evaluating the line integral, we need to pay attention to things. Okay, first, the initial and the destination point must be given. We must have the initial and destination point. Without these 2 points, we cannot find the line integral, because the lower and upper limits for the integration we take it from the initial and destination points. If you have no limits of the integration, we cannot compute the integration. And then the equation of the curve, we must have the equation of the curve. Okay, we must have the equation of the curve. We must have these 2 things in evaluating a line integral. Here, evaluation proceeds by changing all the variables here for finding work done. We are gonna change all variables to parameter t. We change all variables to parameter t. We must have no x and y in the integration, because here we have parameters. We cannot find each x, y, and z as a function of t. Then we replace in the integration, we get a function of t. Then we find its integration, including the initial and destination points. If the initial and destination points are given as x, y, and z, we must convert it to t. We did it before. Okay. We have the properties of line integrals. The properties of line integrals for in xy plane and also in xyz plane are the same. They both have the same properties. We say the line integrals depend on its path. We say if you have, let's say this is the initial point and that's the destination point. The line integral over this curve is different from line integral over this one. It's different from this one, different from this one, different from this one. Okay. This is C1, this is C2, this is C3, C4, and C5. As you see here, we have different paths or different curves. Of each of these curves, we get different results. Okay? Yeah, we say the line integral over C1 doesn't equal to the line integral over C2, and it also doesn't equal to the line integral over C3. That means from a path to another path, the line integral is going to be different. I mean, we get different results. Here, the line integrals on a piecewise curve. For example, if we have, let's say this is the initial point and this is the destination point. If we have C1 to be from here to here, they say this is C1. And from here, we have C2. So the line integral from A to B, this is B, is the line integral over C1 plus the line integral over C2. Okay? We find the line integral over each of the curves, and then we find some. This is a piecewise function or piecewise curve. As you see, this is two parts. One of them, let's say from A to E, C1 is from A to E, and the other one is from E to B. Okay, here it's how to compute the line integral over a piecewise curve. The line integrals around a closed curve, we denote it by this integration. Here we make an integration and then making a circle on it. It means we find that integration of a closed curve. A closed curve, for example, here we have this one. It must be closed. We may have a circle. We may have something like this. We may have a square. Okay, these are closed curves. Over these curves, it's denoted by this symbol. Okay, and line integral is not dependent on direction of the increasing parameter. It's not dependent on the direction of the parameters. Okay, and we now have conservative vector field. Conservative vector field is different from non-conservative vector field. Up to now, we talked about those vector fields which are not conservative. So here, the previous vector fields are non-conservative vector fields. Now we have conservative vector fields. Let's see what are the properties of conservative vector field. We say a vector field F is said to be conservative field if and only if. That means it must satisfy all of these properties. Okay, we say a vector field is a conservative vector field if it satisfies these conditions. First, the vector field is not circulate. That means del operator times F doesn't equal to 0. So this must not be 0. This must not be 0. Okay, and the line integral, this line integral doesn't depend on its path. Here in the above one, we said it depends on the path. From a path to another path, it's different. So in the conservative vector fields, it's not depend on the paths. That means if you have 2 points from this curve, from this, any of these, we get the same result. We get the same result if we go from the initial point to the destination point through any of the curves. We will see how it's equal. You see the value of the line integrals from initial to the destination is the same if we take different paths that commutes between these 2 points. Yeah, that means if we find the line integral of different paths, we get the same results. The value of any line integral of closed curve is 0. The value of any line integral of a closed curve is 0. See, there exists a potential scalar function phi here. We denote the potential function by phi. We denote it by phi, such that if which is the field, equals to grad of phi, grad phi. To determine if a vector field is conservative or not, it is enough to show that at least one of the properties above. Look, we say a vector field is not conservative if any of these is not satisfied. If any of these is not satisfied, okay? So if the vector field satisfies these all properties, we say it is a conservative vector field. But if it doesn't satisfy any of these, I mean, if it's not satisfy at least one of these, means it's not a conservative vector field. We now have the fundamental theorem for line integrals. We say the line integral of a conservative vector field, here f is a conservative vector field, it equals to phi of v minus phi of v. That means here the result is only depends on the potential function. It's only depends on the potential function. And here we just find the potential function. After finding the potential function, we say we find the value of the potential function at the destination point, then minus the value of the potential function at the initial point. Let's say if you have A and B. Here we should first find phi of x, y, z. This is the potential function. Let's say it's x naught, y naught, z naught. This is x1, y1, z1. This is the initial, and that's the destination point. Here, if we have this curve, we find the potential function. The result of the line integral over this curve is phi of b. It means finding the potential function at the point B minus phi of A. That's all. Okay. Here it doesn't depend on the curve. Even on this curve, look, all are the same. We just take the initial and destination point. We don't care about the path which we go from A to B. Okay. Here, the line integral for a conservative vector field, it's not depend on the path, on this path, this path, this path, on all of these paths. We just take the initial and destination point. We don't take the path. We don't work on the path. Since it's that's why we say the line integral of a conservative vector field is not dependent on the path. Okay. And for closed curves, if we have a closed curve, let's say this closed curve, if you go through this curve from this point, so what's the destination point? The destination point is the point itself, is it? It's that so B is here also. Now we say the potential function phi of x, y, z at A and at B are the same. If we subtract phi of B from phi of A, it's 0, because both are the same point. That's why we say the line integral of a conservative vector field over a closed curve is 0. It must be 0. Okay. So that's about the properties. Here It's important to find the potential function. If you could find the potential function, that's all. You just need to find the value of the potential function at the destination point, then minus the value of the destination of the potential function at the initial point. This is destination point and this is the initial point. Here we have an example. It says show that this line integral is independent of its path. That means it's not depend on the path. It's not depend on the path. Here, f is a conservative vector field. We say since f is a conservative vector field, then the integral of a c for f dot dr equals phi of b minus phi of a, where phi is the potential function and a and b are initial and destination point. Respectively. That's okay. So it only depends on A, B, and phi. It's not depend on anything else. It depends on only A, B, and phi. So that's why we say it's not depend on the path. It's not depend on the path. Let's answer for the first part of the question. Hence, find a potential function. Let's find a potential function for the function. Look, we say f equals grad times phi. That means f equals partial phi by partial x plus I plus partial phi by partial yj plus partial phi by partial z k. This is f. And here we have given f. F is p of x, y, z, I plus q of x, y, z, I plus r of x, y, z, j. Z, k. Here, this is f. We equal each components. I mean component I here, we equal to the first component in f. And the second component to the second component here. The third component to the third component here. Then we can find the potential function. Look, we have given that f is this function. This is f. From only f, we can get the potential function. This is f. You see f of x, y, z, or just f. It's a vector field. F equals 3x squared plus 3x squared I. This is a vector. As you see, it's written down in between two angle brackets. Okay, that means it's a vector and they are separated by commas. Yeah, this one is the first component. This one is the second component, and this is the third component. This is for f. We say 3x squared, 3x squared I plus 2, so 6y squared, 6y squared j plus 9z squared k. This is f. This is the vector field which is given. Here we just write down in another form. It's between two angle brackets. When you write down as an equation, we just write down the components I, j, and k for the parts. Okay. This is f, and we say this equals to partial phi by partial x I plus partial phi by partial y j plus partial phi by partial z k. This is the potential function. As you see here, it says f equals grad phi. Grad is partial by partial xi plus partial by partial yj plus partial by partial zk. That's effective. Now we can find the potential function. We equal the first component to the first component, second component to second component, third component to third component. Okay. First, for the first component, we say partial phi by partial x equals to 3x squared. Is it? As 3x squared. Look, this is the coefficient of I, and here the coefficient of I is 3x squared. We equal these two to each other. Now we find phi. This is partial phi by partial x. To get phi, what should we do? We must take the integration for both sides. We must take the integration for both sides with respect to x. Here we have phi sub x. How to get phi? By taking its integration with respect to x. It becomes phi. Is it? And in phi you have x, y, and z. So you say phi of x, y, and z, taking integration with respect to x. In the right hand side, what do you get? To the right hand side, this integration is, it is x cubed plus c. But here we don't add c. We don't add c. We add a constant function regarding the integration. In phi, we have x, y, and z, and the integration is with respect to x. So what are the other variables in phi? They are y and z. We say it's plus g of y and z. Now we find g of y and z. We should find it from other equalities. I mean, here we say partial phi by partial y equals 6y squared. 6y squared. That means here we say we find the derivative for phi with respect to y and we equal it to 6y squared. We say phi sub y equals to what? This becomes 0. This becomes g sub y of y z equals to what? Equals to 6y squared. Let's do it in another way. From the equality of these two vectors, we say partial phi by partial y equals 6y squared. Okay, but here we have phi. We find the partial derivative for phi with respect to y, and we equal it to 6y squared. We equal it to 6xy squared. And we say partial phi by partial y from this function equals to what? The first term is x squared. You have no y in it, so it's 0. And this in the second term we have a function of y and z. We have y in it. We say the partial derivative of g with respect to y is g sub y. Okay, this equals to what? 6y squared. Now, what we say? We take the second component here. The second component here is partial phi by partial y. And the second component here is 6y squared. So partial phi by partial y equals 6y squared. We need to find g of yz. Okay, how? This is phi of xyz. And we say partial phi by partial y equals 6y squared. That means we take the partial derivative for this function with respect to y and we equal it to 6y squared. So the partial derivative for this function, the first term is 0 because here we have no y, it's 0. And in the second term we have a function of yz. We have a function of yz. We say the partial derivative of g with respect to y is g sub y, or partial g by partial y, equals to 6y squared. Now we find g of yz. How? By taking integration for both sides with respect to y. Okay, here g sub y, I mean partial gy partial y equals to 6y squared. How about g? How about g? G is the integration, here we say the integration of g sub y dy equals the integration of 6y squared dy. The left hand side becomes g of xy. Okay, and in the right hand side the integration of 6y squared is 2y cubed plus, now in g we have x and y, we have x and y, but we took the integration with respect to y, so y and z, not x and y, y and z. We have y and z in g. We took the integration with respect to y, so we add a constant function which is g of z. We took the integration with respect to y, and we write down a function to the remaining variables. We have z. Okay, now we put this into phi of x, y, z. Here phi of x, y, z equals x cubed plus g of y, z equals 2y cubed plus g of z. It's 2y cubed plus g of z. This is phi of x, y, z. Now we still have g of z. We must find it. How? By taking, we say, from the third component here, it equals to the third component here. That means partial z by partial k. We say partial z by partial k, so partial phi by partial z equals, it equals to 9z to the power 2, or 9z squared. So this is phi of xyz. That means the partial derivative of this function with respect to z equals to 9z squared. So the partial derivative of this function, the first term becomes 0 because you have no z in it. And the second term also becomes 0 because you have no z in it. In the third term, we have g of z. It becomes g prime. Okay, g prime of z. We say partial phi by partial z equals g prime of z. We say partial phi by partial z for this function. In the first term, we have no z, so it's 0. The second term is 0 also. But the third term, we have g of z. It is partial, its derivative with respect to z is here. The partial derivative for this function with respect to z, the first term becomes 0 because you have no z in it, and the second term also is 0. But in the third term, we have a function of z, so the derivative of g of z is g prime. Okay, because here we have only one variable. We have only one variable. We say it is g prime of z. It equals to what? Partial phi by partial z equals 9z squared. Now we say g prime of z equals 9z squared. How to find g of z? We must take integration with respect to z. Okay, to get g. Here we have g prime, which is the derivative of g with respect to z. We must take the integration with respect to z to get g. Here, g prime of z equals 9z squared. We take the integration for both sides with respect to z. The left hand side becomes g of z. Yes, equals to 3z cubed plus, here we can add c. We can add c because it's a function of one variable. Okay, it is plus c. This is g of z. Now we put g of z here. We put g of z here. So this becomes phi of x, y, z equals x cubed plus 2y cubed plus 3z cubed plus c. This is the potential function. It's how to find the potential function. Only from the vector field we can get the potential function. Okay. Now to find here, it's the potential function. Then it says evaluate the line integral on C. Evaluate the line integral on C. Here, this is the initial point. It says from this point to that point, then to that point, then to this point. Okay. That means we go from 0, 0, 0 to 1, 1, 1. We only take the initial and destination points. We only take the initial and destination points. Here, let's say this is to be 1, 1, 1. And this is to be 0, 0, 0. If you go through this curve, or this curve, or this curve, or this curve, or this, if you go through any of the curves, we get the same result. We proved that before. That means we only take the initial and destination points. So A is 0, 0, 0. And B is 1, 1, 1. So the line integral for f(dr) equals phi of B minus phi of A. What's phi of B? This is phi. If you replace each x by 1, y by 1, z by 1, what we get? We get 1 plus 2 plus 3 plus c minus. There you replace each x, y, z by 0 because it's phi of A. A is 0, 0, 0. And B is 1, 1, 1. That's why we replace each of them by 1. And for A, we replace each by 0. It's 0. Sorry? It's why we did this. Here, this is phi. If you replace x by 1, y by 1, z by 1, what do you get? We get 1 cubed plus 2 times 1 cubed plus 3 times 1 cubed plus c. And if we replace each x, y, and z by 0, what we get? This is the initial point. A 0 plus 0 plus 0 plus c. Here we get minus c. Okay, we get minus c. Minus c with c are cancelled out, and we get 6. That means the line integral is 6. Okay, the line integral is 6, and it's independent from the paths. And here it's given 4 points. We don't care about the points between initial and destination points. We only work on the initial and destination points. Okay. We now have some concepts. Here we have a curve is said to be simple if it's not intersect itself. If it is not intersect itself. Look, this is not simple. This is not simple because it intersects itself. This is simple and that's also simple. And here we have closed and opened. This is not closed. This is not closed curve. But this one is closed curve. It's closed. It is. I mean, yeah. And we say a simple closed curve C has positive orientation with respect to the origin, to the region R. If the region enclosed by C stays on the left of C. Look, if we have this curve, we say the positive orientation means the orientation is counterclockwise. It is counterclockwise. And this is the region. Yeah. As you see, it goes counterclockwise. This is the region R. Okay. So here, since the orientation is counterclockwise, as you see, the region is always in the left of the curve. Okay. As always in the left of the curve. Because the orientation is counterclockwise here. We say a region is said to be connected. A region is said to be connected if we take any 2 points from the region. If we take any 2 points from the region, let's say these 2 points, we can join them by a curve. That the curve is in the region. على curve region كيوتي connected. أجل هل 2 point يور بقدر من الرجل بتوان بكيرف بيك أنا وبستم كيرف كوتيوتي now region كخويه. This one is connected. How about this one? It's not connected because if we take this all to be if both together to be a region, yeah, we cannot join these 2 points such that the joining line or the joining curve is in the region. Look, this part of the curve is not in the region, and it's not in the region. How about this one? How about this one? Is it connected or not? If we take any 2 points, we can join them by a curve which is contained in the region. These 2, we can join them by a curve such that the curve is in the region. So that's connected region. And you have simply connected region. We say a region is said to be simply connected, and every closed curve lying in the region can be continuously shrunk to a point without any part of the curve ever going outside the region. That means the closed curves are inside the region. If the closed curves are inside the region, we say that is simply connected. It's simply connected. And we have simple closed curve. For a simple closed curve, we say if acting on an object and work done needed to move the object around any path can be obtained by the line integral. Especially for simple closed curve, the value of line integral is circulation value of the vector field in the anti-clockwise direction around the closed curve. So here the orientation is anti-clockwise, and the line integral for a simple closed curve, it is the circulation value which is del cross F. It's that this one is the value of line integral for a simple closed curve. Here we will take some more examples about this. We have Green's theorem, and then we have some more examples. Let's take a break for 10 minutes, then we'll continue. We now have Green's theorem. in the xy plane. There is a theorem known as Green's theorem, which can be used to find the value of line integral for a simple closed curve in a plane. Here we use Green's theorem for finding. Green's theorem for finding the value of a line integral on a simple closed curve in a plane. So Green's theorem will let R to be simply connected region whose boundary is simple, closed, piecewise, smooth curve. These are the properties of the curve. Oriented counterclockwise. You say if P of xy and Q of xy are continuous and have continuous first partial derivatives on some open set containing R, then we say the line integral here, this is the symbol for line integral of a simple closed curve. For P of xy dx plus Q of xy dy, it equals to the double integral over the region R for partial Q by partial x minus partial P by partial y dA. Here we use this rule for finding the line integral of a simple closed curve, and it's called Green's theorem. Here we have two examples. In the first one, it says use Green's theorem to find the work done by force field. Here, work done as line integral. We say we talked about this before. We said work done as line integral. So here we just find line integral. That will be the work done. F is this the force field, which is e to the power x minus y cubed I plus cosine y x cubed j on a particle that travels once around unit circle. This is the region. This is the region R. In the anti-clockwise direction, here we have a unit circle. We have a particle. It moves counterclockwise once up to here. It says find the work done. Here we find the line integral. We find the line integral, and we use this rule for finding the work done. Okay, let's do it. Here we have given f of xy was e to the power x minus y cubed. We say f equals e to the power x minus y squared y cubed I plus cosine y x cubed plus x cubed or minus plus x cubed j. It's over this unit circle. X squared plus y squared equals 1. To find the line integral or to find the work done, this is part A, I mean example A. We use this rule. We use this rule. We say the integral of C for P of xy dx plus Q of xy dy, it equals to the double integral over the region R for partial Q by partial x minus partial Q by partial y, partial Q by partial x minus partial P by partial y dA. Okay, so we first should find P and Q. What are P and Q? P is the first component in the vector field. is the I component coefficients. It's the coefficient of I component. Here, P equals e to the power x minus y cubed. And Q is cosine y plus x cubed. And here we should find partial P by partial y. As you see here, we find partial P by partial y. It equals to minus 3y squared. And we find partial Q by partial x. This equals to, this term becomes 0, and we get 3x squared. We now plug in these two to here. Okay, we put this into the double integration of R for partial Q by partial R, partial Q by partial X, minus partial P by partial Y dA. This equals to partial Q by partial X is, partial Q by partial X is 3x squared. You see it equals the double integration of R for 3x squared minus, and this negative sign is for the rule. Okay, then we have partial P by partial Y. Partial P by partial Y is minus 3y squared dA, and this equals to the double integration. Here we can take 3 as the common, we take it out to the integration. We have R over, we have x squared plus y squared dA. dA means dx dy or dy dx. Okay, let's say it's dx dy or dy dx. Okay, now here it's easy to convert this double integration to polar form. In polar, we have r and theta. We have r and theta. We say dy dx or dx dy. This is equal to r dr d theta, and x squared plus y squared equals r squared. We convert like this. Okay, we replace dx dy by r dr d theta, and we also replace x squared plus y squared by r squared. And here this becomes 3 double integration. X squared plus y squared becomes r squared, and dx dy becomes r dr d theta. We talked about this in chapter 3. It's how to convert a double integration Cartesian form to polar form. And it says find the double integration over this unit circle. Let's draw the unit circle. It's 1, 1. It's -1, -1. Okay. Here, R is the radius for the circle. R is the radius for the circle. It's from 0 to 1. Look, the radius here, 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 here. It's all 1. The length of R of radius is 1. So R belongs to 0 to 1. How about theta? Theta, it says 1 round. We start from this point and return to itself. That means the angle is from 0 to 2 pi. The angle is from 0 to 2 pi. So theta belongs to 0 to 2 pi. We have the r and then the theta. That means r is from 0 to 1. Because the radius of the circle is 1. It's a unit circle. And theta is from 0 to 2 pi. We now find this integration. It's easy. Okay? So the most important thing here is to convert the double integration to polar form. Okay? And this equals to 3 integration from 0 to 2 pi, integration from 0 to 1 for r cubed dr d theta. Integration of r cubed is r to the power 4 over 4. It's r to the power 4 over 4. This equals to 3. Integration from 0 to 2 pi. For r to the power 4 over 4, r is from 0 to 1, then d theta. We replace r by 1 first, then by 0. When we replace by 0, you get 0. So we just replace r by 1. We get 3 integration from 0 to 2 pi times, 1 over 4 d theta. We get this. We get this. We replace r by 1, we get 1 over 4 minus, we replace by 0, and we get 1 over 4. Now we take an integration with respect to theta. We take an integration with respect to theta. Or we can move this 1/4 to out of the integration. We get 3 over 4 integration from 0 to 2 pi for d theta. And integration of d theta is theta. It's equals to 3 over 4 theta from 0 to 2 pi. This equals to 3 over 4 2 pi minus 0. When we replace 0 by 0, we get 0. And this equals to 3 pi over 2. This is the line integral. This is the work done for that vector field. Okay? The most important here, how to get this. After this, it's just finding the integrations. It's easy. And for the second example, it says use Green's theorem to evaluate the integral, this integral, where C is the square with vertices is a square with vertices 0, 0, 1, 0, 1, 1, and 0. It doesn't mean that we go from this point to that point. Okay, we find the integration over that square. We find the square. Let's draw the square first. The square is, the vertices of the square are 0, 0, 1, 0, 0, 1, and 1, 1. We join these vertices to get the square. This is the square. We find the line integral over this square, and this is 1, 0. This is 1. This is 1. Okay, and this is 0. So this is x coordinate, and that's y coordinate. So x is from 0 to 1. Is it from 0 to 1? And y is from 0 to 1. X belongs to, you say x is from 0 to 1, and y is from 0 to 1. That means these are the lower and upper limits for the integration. Now, what we do, we have given that the integration of this is p and this is q, comparing to the above one, comparing to the rule here. This one, we have given this. We say the integration of the closed curve C, p of xy dx. The one which with dx is p, and the one which with dy is q. Yeah, this is q and this is p. That means p is y squared and q is x squared. We say the integration over the closed curve C for y squared dx plus x squared dy. It equals to, look at the Green's theorem. It says this equals to the double integration over the region, for partial q by partial x minus partial p by partial y. We say this from this p of xy equals to what? y squared, and q of xy equals x squared. And here we say partial p by partial y equals 2y, and partial q by partial x equals 2x. We say the integral, the line integral over the closed curve C, y squared dx plus x squared dy, it equals to the double integration over the region R for partial q by partial x minus partial p by partial y dA. dA means dx dy or dy dx. And R is the region. This is the region. Over this R, x is from 0 to 1, and y is from 0 to 1 also. This equals to partial, let's write down the double integration. Partial q by partial x is 2x minus partial p by partial y is 2y. This is dx dy. And x, we should write down the limits for x first and then for y. X is from 0 to 1. And y is from 0 to 1 also. Now we take this double integration. We take this, first we take the integration with respect to x, and then with respect to y. If we take the integration with respect to x, we get the integration from 0 to 1. This is the integration, the limits for integration for y. With respect to y, I mean. The integration with respect to x is x squared minus 2xy. It's from 0 to 1 for dy. If you replace by 1, we get 1 minus 2y. And when we replace by 0, we get 0. And this equals to the integration from 0 to 1 for 1 minus 2y dy. Now we take an integration with respect to y, and we get y minus y squared from 0 to 1, and we get 0. That means the line integral over that curve, over that region is 0. Okay, over the region R, which is that square is 0. So this is answer for the second part. And you have surface integrals. In this chapter, it's the last chapter. Chapter 7 is the last chapter of this semester. And in this chapter, we have 4 sections. In the first section, we just talk about surface integral of a scalar field. In the second one, we have surface integral of a vector field, then Gauss theorem for surface integrals and Stokes theorem for surface integrals. Okay. Here, surface integrals can be done by using this integration, this double integration. Here, sigma is the surface. We denote the surface by sigma. Before, for the plane or the region, we denote it by r. But now we denote the surface by sigma. For f of x, y, z, ds. Now we have this theorem. It says let sigma be a surface with equation z to be g of x, y. F sigma to be the surface with equation z to be g of x, y. Yeah, this is the surface. Okay, we say the surface integral equals the double integration r of xy. R of xy is the projection of the surface on the xy plane. It's the projection of the surface of the xy plane. That means we say if z to be g of xy, if z to be g of xy, we use this rule for finding the surface integral. As the double integral over the region R over xy plane. R is the projection of the surface on the xy plane. For f of xy, and we replace z by g of xy, we have to be given this. Okay, that means here f is a function of x and y only, and multiplying by the square root of partial gy partial x plus partial gy partial y squared, both squared plus 1, then dA. This dA means dx dy or dy dx. And if sigma to be a surface with the equation, if you have given this equation, y to be g of yz, g of xz, if y to be g of xz, here we say we find the double integration for over the region R on the xz plane, as we have y to be g of xz. Look, if z to be g of xy, we find the integration over the region xy, or the projection of the surface on the xy plane. But here, if you have given this, we find the integration over the projection of the surface over xz plane. And we say it is f of x, and we replace y by g of xz. That means we must have only x and z in the function f. We must have only x and z. Okay. And here we replace y by g of xz. That means here in f we have only x and z. Then multiplying by partial gy partial x plus partial gy partial z, both squared plus 1 dA. But if we have given x to be g of yz, if x to be g of yz, here we must have only y and z in the function. That means we replace x by y is g of yz, and here you are y and z. Multiplying by the square root of partial gy partial y squared plus partial gy partial z squared plus 1 dA. We use these three rules for finding the surface integral for over the projection of the surface. If the projection is on xy plane, we must have only x and y in the integration. If the projection is on the xz plane, we must have only x and z. And if the projection is on the yz plane, we must have only y and z in the integration. Here, how to know that it is on whose plane? By this function. Here, it's x equals g of yz. That means it's on yz plane. It's on yz plane. That means we must change x to g of yz. That means we must have no x in the integration. We must have no x in the integration. And here, we must have no y in the integration. That means we replace each y by g of xz. And here, we must have no z in the integration. So we replace ez by g of x, y. And you have some examples as for next lecture.